All right, looks good. So you guys all have a sheet in front of you that is titled Parent Functions. Where in the world? Oh. Where this is probably the most organized my desk has ever been. And yet I can't find my pencil. Why do I own like 1,000 mechanical pencils. Why do I not just have oodles of them available everywhere? Anyway, okay, so what in the world is a parent function? It's basically exactly what you think about. It is a function which we can then take and manipulate, not that you manipulate your parents, but anyway, you start off with a parent function. It's basically the simplest version of that function, and then we can do things to it. Flip it over, move it left, move it right, all sorts of things. Stretch it, shrink it. So that's kind of what we're going to be talking about over the next couple of days. So before we can do that though, we need to have an idea of what the parent functions look like. So let's just start with the first one. If you have y equals c, c is just some number, okay? Any number. I know you know what that looks like. If c is equal to any number, what kind of a line is it? It's just a horizontal, yeah. So just pick a horizontal spot to put it. Horizontal line. Okay, and that could be at any y value. Now these linear ones, how do you graph y equals x? Jake? You're right, you're gonna start at the origin, and then where do I go? Yeah, the slope is 1, right? The y-intercept is a 0 because there's nothing there, and the slope is 1. So this is that perfect diagonal that goes right through the origin and goes forever in both directions. Okay. So there's that one. So we can basically, any linear equation that we graph, we could get there. I mean, I know we have our ways, y equals mx plus b, but you could get there using the things that we're going to learn, the transformations that we'll be doing. Okay. Quadratic. Y equals x squared. So that's your most basic form of a quadratic function. What do those graphs look like, Braylon? That is a parabola. And where does it start? Yes, these start at the origin. And then I know you guys have your way that you learn. This is how I learn. You can do whatever you do, but I go up 1 over 1. And remember that parabolas are always symmetric. They have that axis of symmetry. So whatever you put on one side, you can mirror over to the other side. So I go up 1, then I go up 3, mirrored over to the other side, and then you can go up 5, mirror over to the other side. Again, even if you forget it, it's not a big deal because you can always just plug in numbers, right? If you're not sure what this graph looks like, plug in 0, plug in 1, plug in 2, plug in 3, and so on, and so on, and so on. And it will create this beautiful parabola for you. It's helpful to know that it's a parabola. It's helpful to know that you have, it's going to be the same on both sides of that axis of symmetry. So definitely helpful. So cubic, you may or may not remember. Or do you? Well, it does do some things, but.
Like it hits the x-axis twice.
What? Go ahead. No, that's what x to the 4th. So x cubed, Laura?
So like,
Pretty much, yeah. It's like this kind of long drawn out s. So let's plug in some, if I take 0 and I cube it, I get 0, right? What do you get when you cube 1? 1. So 1, 1 is going to be another point. What do you get when you cube -1? Yeah, so negative one is another point. But now, so I know you might be thinking right now, this is just going to be a straight line. No, it's not, because when you take 2 and you cube it, what comes out? 8. So 2 comma 8 would be another point. That's right at the tippy top. And when I cube negative 2, what do I get? Correct. So now hopefully you can see. And when you connect these, it's a nice smooth curve. We're not going to make things jagged. This is not connect the dots like you did when you were a kid. I mean, it kind of is, but you want to connect them smooth. There's no jagged edges here. So that is what y equals x cubed looks like. So it's like the slithering snake. All right, what do we got on the back? Oh, absolute value. What's that one? Kinsey? Yes, it's that V shape. So you're going to have your vertex at the origin.
Please pardon the interruption. Cameron Chisholm, please report to the tech office. Cameron Chisholm, please report to the tech office.
Okay, this one is at sharp V. So if it's just y equals the absolute value of x, you're just going to go up 1/1 on one side. But on the other side, the slope of this branch is a -1. So we're going up 1, back 1. Those two are always going to have the same slope. It's just that one of them is positive, one's negative. So this comes out to be a nice V. Which, by the way, I mean, you could get this by just plugging your values in. So the absolute value of 0 is 0. The absolute value of 1 is 1. 2 is 2. Then when you go negative, if I plug in -2, isn't the absolute value of -2 +2? It sure is. So that's how I get these kind of going back up again. All right, square root. Anybody remember what this one, Jake?
So it almost looks like what 1/2 of a parabola would look like, but if the positive square root function, then it's just gonna be going to the first quadrant and then on.
You are correct. So this thing, let's assume that you have no idea, right? You can always get them by plugging in some points. Can I plug in a negative number though? No, right? Because I can't take the square root of a negative. So in this case, we'll eventually talk about the domain of these. I can't have any negatives for this function. So I'm going to start at 0. Square root of 0 is just 0. When I take the square root of 1, what comes out? When it's already written, so I'm not taking the square root. So this indicates you're just considering the positive root. If they wanted both, they'd put the plus minus in front of it, but I don't have that. So if I take the square root of 1, it's just 1. So 1, 1 is another root. You could figure out what the square root of 2 is, but why would you want to bother? Why wouldn't I just pick numbers that are nice for me? So what should be the next number that I plug in? 4. If I plug in 4, I get out a 2. So 1, 2, 3, 4, I get out a 2. And then we'll see if we can do one more. The next one will be 9. Yes. 6, 7, 8. So if I went one more, that'd be 9. And we'll come out with a 3. So your square root functions look like this. They start at the origin and then they kind of go up and over. I do want to point this out. This is increasing forever. So this will continue to go up and up and up and up. It just goes slow. It goes kind of quick at first and then it tapers off, but it is going to continue to go up forever. It's just going to take a really long time to get there. So if I were to ask you the range of this thing, what would you tell me? What's the range of this graph? Raylan, go for it. Yes. Greater than or equal to 0 for the y, right? The smallest y I have is 0, and then it's going to continue to infinity forever. Just really, really, really slowly.
I was thinking in terms of
Oh, so then you could do
0 bracket 0. comma.
We've got it. So there's square root. It doesn't have a cute name like parabola. I call it a slug. You call it whatever you want. Because doesn't it kind of, right? If you give it a little eyeball and a smile and an antenna, right? It's kind of like a little slug, just crawling along. But you do you. Okay, what's next? Oh, have you ever even seen this before? Has anybody seen it? You have? Anybody else? Greatest integer. Jake, tell us what it is.
I think that's where almost like you have like a great like an integer that is that
Basically, so if this is essentially a rounding graph. So if I wanted to ask for the greatest integer function, it's going to be the greatest integer less than or equal to the x that you have. So the greatest integer less than or equal to what you have. So if I wanted to plug in, let's say 1.2. What's the greatest integer less than or equal to 1.2? Okay, rewind. What are the integers? What are integers? Jake?
numbers that are written on a line that are numbers and irrational.
You're close. You're right about the whole numbers. Did you say and rational?
Yeah.
They are rational, but so integers are rational numbers, but are all rational numbers integers? No. So the integers, ladies and gentlemen, they're just whole numbers or a negative whole number. That's all it is. So if I say, how many integers are there in between 4 and 6, you would say 1, right? 5. If I said how many numbers are in between 4 and 6, isn't there an infinite number? Right? Because you could have 4.1, 4.2, 4.3, forever. So integers are whole numbers or they're negatives. So if I give you the number 1.2 and I ask you, hey, what is the greatest integer less than or equal to 1.2? Mackenzie, 1. So check this out. That's a point we just found. If I plug in 1.2, it's going to spit out a 1. What happens if I give you 1.7? What comes out? I want, remember, the greatest integer less than or equal to that number. So what is the greatest integer less than or equal to 1.7? 1 still. You're always rounding down. Okay, so what's basically going to happen here is that from 1 up until you hit 2, you have a flat bar. When I plug in 2, if my number is 2, the biggest integer less than or equal to 2 is 2. If I plug in 2.3, what comes out? 2. I want you to think of it almost in terms of money, right? If you had to pay for something, let's assume you could always give exact change. If your bill was $2.70, you need 2 whole dollar bills and then coins, right? If the bill was $2.01, I need 2 whole bills plus some coins. So it's basically how many bills would you need if you're going to pay for this item, assuming that that's your total, has some change in it. You know what I'm saying? So if you had a total that was, I don't know, $9.17, what would your greatest, what would the greatest integer be? 9. If it was $9.99, what would it be? 9. It's still 9 because I need 9 whole dollars and then change. So it's really kind of asking you, how many whole dollars do I need if I'm paying this bill? So what does this end up looking like? It's kind of like this whole little series of stairs. Notice I'm having open circles and closed circles. Oh, great question. I'm going to zoom in a little bit. Let's do it for the decimals. What if my bill was 25 cents? How many whole bills do I need? 0. So this one is still going to look like this, right on the x-axis. Mackenzie. So let's say we were trying, oh, I don't know. How about negative 25 cents? Oh, wait. Oh, yeah, now it's all messed up. Well, it just keeps going like this, but now my money example doesn't make any sense. So I guess you can't apply my money logic when we get down here, because you wouldn't be paying for these things. It just keeps going. Oh, I skipped one. So I guess just start it in the positive and then continue in the negatives. So let's add also to our notes right here, just so we remember. This is the greatest integer less than or equal to. So now forget my money example. Let's just, oh, sorry. I didn't even realize it, couldn't see that. Let's just try that following the definition. If I plugged in something like -1.5, right? So -1.5, what is the greatest integer less than or equal to -1.5? -1 is greater, right? So it'd be -2 is the greatest integer less than. So yeah, my money doesn't, I can't think of it how that money would translate in the negatives, but hopefully that makes sense.
Stairs, like if you're halfway up the first stair, you're still on the first stair.
Oh, I like that.
Okay.
Yeah. Yeah, that definitely works. So any Hoosers, that's what those are. Greatest integer function. They're so cute.
Or if you're like floors.
So just make sure, I'm gonna zoom way in so you can just make sure that you have what I have, because oh my gosh, with this. Wrong way. There, oh, that's better. I just want to make it crystal clear that I have open circles here. So again, if you do the vertical line test, this is still a function, right? As you go, and I got lazy, I stopped, but it just keeps going forever. Okay, so make sure that you have on your paper open circles and closed circles. And you should never have two closed circles on the same vertical line, because now it's not a function anymore. Okay, and then the last one that we need to talk about is the reciprocal function, which we have talked about a little bit in this class before. So if you take a look at it, 1 over x. What value am I never allowed to plug in for x? 0. So that creates, what's the name of that thingy? That line that we put in there. Do you remember? Has a funny name. Sounds like a square, but it's not. What did you say?
I don't know. You said squall.
Oh, squall? No.
You said square, so I was like, right.
Braylon?
Asymptote.
Asymptote, yes.
Like a square.
So, asymptote. There's the word, okay? So remember, we have talked about this. It's not part of the graph. That's why I did it in another color, but it is nice to have it there visually because you're going to see your graph will get ridiculously close to this asymptote, but it'll never actually touch it. So it just keeps getting closer and closer and closer and closer, but it never actually gets there. So let's plug in some points. If x is 1, what's 1 over 1? 1, right? So 1, 1 is a point on my graph. Okay, cool. If I plug in 2, though, what comes out? 1/2. So when you plug in 2, 1/2 is now a point. And now you can probably see what starts to happen. You plug in 3, you get a third. You plug in 4, you get a fourth. You plug in 100, you get 100. So see how it's getting super, super, super close down here. So you actually end up having another asymptote that we didn't even talk about yet. But it's going to get ridiculously close here. But now let me ask you this. What if I had plugged in a number in between 0 and 1, like a half? What do you get when you plug in a half? If you have 1 over 1/2, what is it? It's 2. So 1/2 spits out a 2. So if I did the same thing, if I plugged in 1/3, wouldn't it come out with 3? 1/4 would come out with a 4. So look at what's happening. This side's going to get closer and closer and closer and closer and closer. It's just going to keep going forever, but it will never actually touch my asymptote here. Can I plug in negatives? Sure, why not? There's nothing stopping you from having a negative. It's just a 0 I can't have in the denominator. So I can do the same thing. If I plug in -1, doesn't the whole function just become -1, right? So -1 is a point. And then basically you have the same situation. You plug in -2, now it's -1/2. Plug in -3, now it's -1/3. So you'll be able to see that this side is going to get ridiculously close to the x-axis here. And then the same thing happens in between 0 and -1. Plug in -1/2, it would spit out a -2, -3, and so on and so on and so on. So this is your parent function for a reciprocal. I'm also going to put in, I'll just make the x-axis pink here so we can see both asymptotes. Isn't that something? So they'll just get super close to those values, but never actually touch it. But everything else is fine, right? I can have anything else, just not 0. And because I can't have 0, there's actually no way for me to get a range equal to 0 either, is there? Right? Right. Okay, any questions? No? All right, so let me give you, this is your homework, but I'll do maybe 1 and 2 of them with you.
Oh, this is a little.
Oh, part of the problem?
Yeah.
Oh, it did. I think it was just an F. Yeah, just an F. Okay, guys, sorry, I hole punched away part of number 1. It's just an F that goes before that X. So we'll just read f of x equals 4.7. So, I mean, we can do a really easy one together and then we'll do a harder one together. So basically you're just recreating that parent function. If you plug in a -3, it's just a constant. So no matter what x value you plug in, isn't this just a horizontal line at 4.7? 4.7. There's my best approximation of 4.7. So no matter what x value I get, I'm always getting out 4.7. No problem. All right, so what's the domain of this thing? All reals. What's the range? Yes, y is only equal to 4.7. I don't have any other values. Would this thing be even or odd? Or neither, I guess, is an option too. So remember what they are. Even has to be symmetrical over the y-axis, and odd would have to be symmetric over the origin. What'd you say? C? I heard C. C's not a choice. Oh, I could have sworn someone said C. Does this have even or odd symmetry? It has even, right? If I folded that thing on the y-axis, doesn't it match up? Yeah. Oh, sorry. This one has even. What's the x-intercept of this thing? None. Where's it decreasing? Nowhere. Increasing? Nowhere. Constant over which intervals? Yeah, all of them. So I would say -infinity to positive, right? Oh, why do I ask for this? Oh, okay. X-axis, y-axis, or origin symmetry. Which one do we have? We have y-axis. Any relative mins or maxes? No. Okay, so there is an easy one. Should we do the greatest integer one together? Since that one's a little bit trickier. Okay, let's start by filling in the chart. So this is number 8 on the back. What is the greatest integer less than or equal to 0? 0. How about 1/2? 0. 1/4. 3/4. 1. What's the greatest integer less than or equal to? 1, right? If you go to the store and your bill is $1, you need one whole dollar bill. What about if it's $1.40? What's my greatest integer? I'm hearing it. It's a 1. What about 1.9? Still 1. You want the greatest integer less than or equal to what you have. All right, we already kind of know how to graph this, but you could use the points that you just found to help you if you needed it. So we know it's these cute little steps. If you want to use a scale and sort of change it, you could, but I mean, you don't have to graph every single line. Just give me enough that you can see. I'm gonna do them all, but if you don't want to, I understand. I like to have them all because that helps with domain and range stuff, I think. Do a quick scan, make sure you don't have any 2 closed dots on the same vertical line, which I don't. Looks good. Okay, so now let's talk domain. What would your domain be? Understanding that this just continues forever. It's all reals, isn't it? You can get from the left-hand side to the right-hand side horizontally without ever having to jump horizontally. You move up and down vertically, that's fine, but I don't have to jump horizontally. I can get from one side all the way to the other, no breaks. So this would be all reals. How about the range? What would your range be? Let me ask you this question. Is the range all reals? So let me ask you, if the range is all reals, do you have a Y value on your graph of, I don't know, 1.5? A Y value of 1.5? I dare say you don't. Do you have a Y value of 2.7? No. So your range is not all Y values or all reals. Because I don't have any Y values in between them all. Uh-huh. Well, all integers. So what we can do, instead of like literally listing, I want you to list all the integers for forever, you can just say that Y has to be, do you know this funny looking E thing? Have you seen that before? That just means is an element of. And then what's the one for all integers? There's a letter. What's the letter for integers? Is it Z? I think it's Z, right? We're gonna say Z. Let me look. Oh yeah, Z. See how we have that funny looking R for all reals? There's a funny looking Z, which stands for all integers. So if you just want to, I mean, if you forgot that on a test or something, literally, you could just write all integers instead of the letter. But it's kind of fun to know it. That symbol for all integers. Do you know why it's a Z and not like an I for integer? Like we have R for rational. Or not even, no, real, sorry. R for real. Y is integer Z. Evan, you know? I don't remember, to be honest with you. I think so, that makes sense. But Y is integer Z. Oh, you're saying because it's already used by irrational. I actually believe that's because it's just in a different language. I think it's the word for integer, and I think it's German, starts with a Z. Yep.
So I is supposed to use represent, so it's imaginary number, so have the same simple represent.
True.
Different concepts.
Yes. So how they landed on Z, I believe, is the word in another language. Anyway, so there it is. So does that make sense though, that why it's not all reals? Because you don't have Y values at every single Y real number. You only have them at the integers. Okay, is this thing even or odd? Let's start with even. Is it even? If you fold over the Y-axis, does it match up? No. If you folded it twice over the Y and the X, would that match up? Yeah, so this does have, oh, wait. I actually don't think that it would. I think you'd have the open dots on the closed dots, right? If you flip this one over, you'd have an open dot here, and then if you, yeah, your open and your closed circles would not line up. So this one actually has none. X-intercepts. Where does this thing cross the X-axis? Hi. Okay. I say, okay, go ahead. So 0 is one of my answers. Doesn't it cross everywhere in between 0 up until I hit +1? So all of those are my X-intercepts. So I would write that as from 0 until 1, but that's smooth parenthesis because I don't want to actually include 1 because 1 itself is not part of my X-intercepts. Where are we decreasing? We don't. Where are we increasing? We still don't. even though I know like the graph goes up, but each piece of the graph, you need a continuous piece of the graph that's either moving up or down. I don't have that. I just have boop and then boop and then boop and then boop, right? So I don't have increasing anywhere. Constant, that's what I have. I have it being, let's see. So this is kind of a funny way to write this. Constant over which intervals? From n to n plus 1, where n is an element of the integers. Oh, sorry. So let's think about what this means. This is saying, this kind of gives me all of them in one sort of a one-stop shop. I am constant from, pick a number, let's say 3. So I'm constant from 3 to 4. Then again, if I plug in 4, I'm constant from 4 to 5. And again, from 5 to 6, and so on forever. Which symmetry do we have, if any? We have X? No. Y? No, we already said that. So do we have origin? We said no, right? Because the dots wouldn't line up. So this would be none. Any relative mins or maxes? Nope. Okay, so that's the idea. So we did an easy one and a hard one. If you guys could finish the rest of them. Anybody have any questions right now? Okay. I will go open this on Jupyter. I already have that. Yeah, so your phone in the box for me, please. Okay, let's stop this.